Hi everyone, it's Dr.Oefelein. I'm sorry I couldn't be there, but hopefully this presentation will be just as interesting trying it this way. So the title is Effects of Real Fluid Thermodynamics on High Pressure Fuel Injection Processes. And my co-authors include Reynolds Doms and Guillaume Localized, who are both now staff at the CRF, and Anthony Ruiz and Lael Hakim, who are both postdocs. And the support for this work was out of the DOE Basic Energy Sciences program and Vehicle Technologies program. So in this presentation, there's two objectives. The first is to summarize a new theoretical description that aims to quantify the transitional effects of real fluid thermodynamics on liquid fuel injection processes at the typical engine operating pressures. And then second, I want to highlight the coupled effects of real fluid thermodynamics at these conditions using LES applied to the spray A experiment, which I'm sure most of you are familiar with, and nonetheless I'll describe in more detail in later slides. The effects of pressure on liquid injection processes are really not that well understood. And the two images on the left more or less highlight the key differences that occur as you go from what we might call low, near critical, and even supercritical pressures to higher supercritical pressures. So what I'm showing here is a shear coaxial injector with liquid nitrogen injected at the center and surrounded by a helium injector. So it's meant to resemble something like a liquid oxygen hydrogen injection at rocket-like conditions. Of course, this is laboratory scale. And what we see is at the lower pressures, something that looks like classical atomization. And as we go higher and higher in pressure, and temperature plays a role in this too, we go from classical sprays where we see drops to diffusion-dominated mixing with exceedingly large gradients, such as the image on the lower left. And so the question is why? What's really causing that? And to date, while we've had a lot of imaging to show that these two extremes exist, there's not a lot been done in terms of trying to explain precisely what's happening beyond the notion that things like surface tension are becoming diminished and those types of things. So the first part of this talk is an attempt to explain at least some factors leading to the why. So let's consider the Sandia spray A experiment by Lyle Pickett. And we'll come back to this later, but for now, on the left is a photograph of the vessel. On the right, I list some conditions. We'll come back to those. But let's move to the next slide. And what I really want to highlight to start is the fact that direct injection processes in this experiment exhibit similar behaviors. And that is to say, this is liquid endodecane injected into essentially nitrogen or nitrogen and oxygen, depending on the case. And what we see drops when the endodecane is injected at 363 Kelvin and 30 bar, and we stop seeing drops at a case where when we move to 60 bar. So this presents a dilemma from the phase equilibrium perspective, and that's what I want to talk about on this slide. So here we have temperature as a function of mixture fraction, and on the plot are the two equilibrium curves associated with the injection conditions that I just talked about on the last slide. So we have the vapor equilibrium curve associated with the 60 bar case where we're injecting endodecane at 363 Kelvin into a 900 Kelvin ambient. And likewise, we have the same for the 30 bar case at the lower temperature and pressure conditions. So I'm going to refer to those two interfaces as the low temperature and high temperature interfaces. Now, also on this plot, I'm showing two mixing lines. So if you follow the 60 bar mixing line, and we derive these by just assuming adiabatic mixing, and then you can follow that line down to where it intersects the equilibrium curve at 545 K for the 60 bar case. And so that represents what we might call the interfacial temperature for these conditions. If we just assume adiabatic mixing is a good assumption, which it turns out to be for this case. Likewise, in the lower left, you can see the mixing line associated with the 30 bar, and that intersects at a temperature of 428 Kelvin. And the initial ambient was 450 K for that case. So there's a few observations you make. One is the low temperature interface, we know we see drops. The high temperature interface from the imaging, we know we don't see drops anymore. And the last thing on this slide is, if one wanted to argue the reason we don't see drops is because we've exceeded the critical points from a phase equilibrium perspective of that system, what you find out by looking at this is that would require non-physical mixing, which just can't occur. So we wanted to understand a lot better what's going on with the interface, the properties associated with the interface, such as surface tension and so on. To do that, we're going to apply gradient theory, and that's what I want to describe next. So what I'm showing you in this plot is essentially the exact same figure as the last plot. Only now what I want to focus on are the low temperature interface and the high temperature interfacial states. And in particular, we want to use those states as the boundary conditions for application of gradient theory, which is then what we use to analyze the interfacial structure. And the details associated with that and how we did that and why gradient theory is appropriate are provided in the paper that I cited at the bottom of this page. But for now, suffice it to say that ideally one might want to perform molecular dynamics simulations. Gradient theory is the next best thing at significantly reduced cost computationally, and provides the same type of information and has been validated for use in at these types of conditions. So with that, let's look at the final results we get when we apply gradient theory in terms of the interfacial structure. And I've just kept this very simple for now because I only want to highlight a few things. So the first is, if we look at the conditions where we know we have drops, we see a lot of things we expect. For example, if you look at the top of the plot, you see the surface tension is 12.2 millinewtons per meter. You're looking at the profile of density across the vapor-liquid interface. We see that the interface thickness itself is about half a nanometer. The mean free pathway is about 0.92. For reasons which will become apparent on the other half of this slide, that gives us a Newton number of 1.8. And typical wisdom or approximations, and anything over about a Newton number of 0.1 implies that the interfacial itself is molecular in structure, and that's exactly what we expect. Now what's interesting is if we go to the condition, the high temperature interface, we start seeing some differences, and they're somewhat surprising, at least initially. First, if you look, we see the surface tension is now smaller, but certainly not diminished. So there's still residual surface tension effects at these conditions, even though, as I mentioned previously, we don't see drops. But what else is interesting is we see that the interface thickness itself has increased to 2.3 nanometers, but the mean free path, because of the increase in pressure, has decreased. And that combination has led to a Newton number that's 0.05 for this case, which starts to imply, because it's less than 0.1, is it's more of a continuum than not. So the conclusion, when you do a lot of analysis, is that the transition from spray to diffusive mixing occurs through a combination of broadening interfaces, reduced mean free path, and vanishing surface tension. Now there's one more catch to that, in that what really is going on, and this requires some further work on our part, we're looking into these things now, is once the interface thickens to a certain point, as you're going up in terms of these conditions. And so now what I'm showing you is kind of a diagram that now includes, at these different conditions, what the estimated Newton number is as we move up. The dotted line in between the 60 bar and the 30 bar, so at the 52 bar vapor-liquid equilibrium curve, is showing you where the Newton number is 0.1, and that's just a rough estimate. It's not an on-off switch. There's a continuous change across this interface. And what we suspect is really happening is once the interface thickens to a certain point is really non-equilibrium thermodynamics kicks in. VLE doesn't hold anymore, and that's really the process. So there's a time scale associated with this that we still haven't defined or quantified, but those are things we're working on now. So the point is, once we get to, say, some place in the vicinity of the Newton number 0.1 regime, really what happens is disintegrates. You end up with more of this picture now, where I'm showing you a mixing line that doesn't end at the VLE point anymore. It applies across the whole regime because the mixture, even in the vicinity of what used to be the interface, is now just part of the continuum. The governing equations apply across it, and it's really just a more or less exotic mixing process that's being dominated by the real fluid thermodynamics. And that's what we assume here. So what the theory also lets us do is to look at this problem from the standpoint of a regime diagram. And that's what this plot is intended to show. So here we have endodecane. It's assumed that it's being injected at a temperature of 363 Kelvin into nitrogen. And we're looking at what happens over a range of typical ambient temperatures and pressures. And superimposed on this plot are representative Newton number contours. And so here we're showing 3. We're showing the 0.1 just as a reference, and then times 2 and divided by 2. And so the point with this diagram, there's a few points one could make. First, if you're in the lower left, you can be somewhat confident that you're in kind of a classical spray regime in whatever system we're in. And likewise, if we're in, far over to the upper right of this plot, one could say, okay, I think diffusion-dominated mixing is probably a really good assumption. But something we have to be careful about is the Newton number lines here are just, again, it's not an on-off switch. So this transition occurs over some time period and over some continuous range of Newton numbers. And so once we get down to, say, within these bands in the vicinity of 0.1, we have to be careful because what's really going on is we have things associated with both types of systems going on at the same time. And I think that's a new area that needs to be looked at closer. And the reason for that is if we start looking at typical conditions here, for example, for diesel engines, what you see is that this plot suggests that a lot of diesel engine cycles are operating kind of more in the diffusion-dominated regime than not. And that's true for some other devices too. And so one thing we're interested in now is really trying to understand how this transition really occurs from a non-equilibrium perspective, and what are the nuances with that in terms of modeling. And I'll say a little bit more about modeling in the coming slides. But here I just want to close or round out this talk by saying this has also allowed us to help inform the experimentalists. So here Lyle Pickett and his group on interesting places to look to try to see if we understand when we have diffusive mixing and when we have classical sprays. And so now I'm showing you the same plot populated with experimental points, where green represents where they tended to see drops, and just based on just being a consistent criteria, which could shift things a little bit when they don't see drops. And there's a lot that goes into that due to the challenges with even detecting drops at certain conditions and so on. So this is all ongoing work, but I want to give you an idea. So at the point indicated by the arrow, here I'm showing you that's a typical movie that they get from their imaging. So you're looking at essentially shadow graphs, and there you can clearly see drops. And likewise, if I move to this and we play where now I'm showing you a region where they say they don't see drops, you can see the differences in the imaging with that. And again, there's more references on this, and I'm listing the top 3, where the most recent one was at the Combustion Symposium at the bottom there, where we're starting to try to understand this from a non-equilibrium gas-liquid interface type of perspective, but that's ongoing work. Now what I'd like to do for the second part of the talk, which will be a little bit shorter than the description I just gave you, is really now I want to apply a real fluid model within our LES and see what we can understand and just see what we can learn about some of the nuances of these types of flows. So this is just a rough example. This is something we did as part of some gas turbine work. Here you'll see very similar conditions. We have a liquid and decane, air, jet, and crossflow. The Reynolds number associated with the jet is 100,000, and with the crossflow is 620,000, and that's due to the fact that the pressure is 60 bar. So here we assume we don't have drops. We're applying real fluid thermodynamics within our LES solver, and we're interested in several things. Some of the general questions that come up with an LES, like what level of resolutions do you need to resolve different quantities, and how much resolution is enough. And here I'm showing a highly resolved LES where even the scalar dissipation field is to some degree being resolved well, but of course we have to quantify what that means. I don't want to spend a lot of time on this slide at all, other than to highlight the fact that the theoretical numerical framework we're using in our solver is really aimed at 3 things. One is comprehensive physics involving the fully coupled compressible conservation equations, real fluid equations of state that handle the high pressure phenomena, such as that described in the previous slides. With that, the corresponding detailed thermodynamics and transport, and so on. That's point 1. Second is we're doing the best we can to maintain high quality numerics, and there's a lot we could discuss there, which I'll defer for now. And of course, last is we work closely with across the full hierarchy of platforms, from local clusters to some of the bigger DOE platforms. I'll mention that all the calculations I'm showing you here were pretty much done on high-end clusters on the order of with 5,000-ish cores. In the calculation I'm about to show you, and also in the jet and crossflow that I showed you as an introduction to this section, we calculate real fluid mixture properties using the extended corresponding states model. That gives us a multi-component formulation that makes use of either a BWR or cubic equations of state. The cubics are Peng-Robinson or Suave-Retilich-Kwong, and in these calculations we use the Peng-Robinson. So this theory has been generalized to treat a wide range of hydrocarbon mixtures associated with the fuel oxidizer product system of interest. It's based on both theoretical and semi-empirical data, and here we just have them coded into custom routines optimized for LES. And having said that, everything we're doing in terms of property really keys off of the body of research that NIST has done over the years, and of course we use that body of work to validate our models also. Now let me switch over and focus on LES of the Sandia spray A case. And so what this slide is showing is the computational domain of the Lyle Pickett's high pressure combustion chamber. Here again, we're injecting endodecane at 363 Kelvin into the ambient chamber that I'm showing in the purple color, where the initial conditions are 60 bar, the temperature is 900 K, and essentially this case is non-reacting, and we're interested in the mixing field and so on. So this slide shows the transient evolution of the jet for that case, where we're focused on, again, trying to understand this from a detailed structural flow interaction perspective. And the most recent work in that area was shown at the symposium in the paper that I'm citing at the bottom of the slide. This just gives you an idea of what the flow field looks like. The first step, of course, is to do what comparisons we can with whatever data is available. And what I'm showing here is just a simple comparison with the penetration data, where if we look at the upper curve, so the solid line, that shows the penetration associated with the vapor. And then you're seeing the two curves towards the bottom of the plot, where depending on what threshold we pick in mixture fraction, we are either closer or farther away to what was measured in terms of the liquid core length. And that's an interesting problem to look at, especially when you, from the real fluid thermodynamics, because really what we're looking at there is a very steep gradient. And of course the optics can't really distinguish between a gradient and a liquid interface at these conditions. So there's some effort there going on into trying to help, and this will take a while, but trying to help on the interpretation of what some of the imaging from the experiment is producing. And hopefully that'll get better over time. On this slide, I want to show one interesting example of some of the analysis that we can do with the LES beyond what we can get from the experiments, especially in the context of real fluid mixing and so on. So here what we're looking at are the sound speed or contours of those on the top plot, and its corresponding scatter plot on the right side. And then the bottom contour plot is the Mach number. And what you see is there is a fairly wide variation in the sound speed, which ends up inducing a fairly large variation in the Mach number. And that is simply because, if you think it through, that we have hot ambient gas that's mixing and being cooled with some of the cold fuel, but still kind of retaining the more nitrogen-like characteristics in terms of sound speed. So that causes a huge drop in the sound speed, which then is what gives rise to the large Mach numbers. What that ends up doing from a flow perspective is we start seeing pockets of localized supersonic regions, and due to this wide variation in sound speed. So even though one might think this is somewhat of an incompressible flow problem, the variations in properties, and this is just one example, really make it highly compressible, even though the bulk, if you just look at the bulk flow Mach number, it's really around 0.5. So those are some of the things that become more interesting when you start looking at the mixing field and highlighting the importance of including these compressibility effects. So this translates to a plus or minus 5 bar variation in the pressure field locally. Okay, so I want to close this out now, and I want to highlight one last example of what we're trying to do. The other thing we're looking at, and I'm just going to put these images up here, is now we want to analyze the flow field to start understanding what the local mixture state looks like just prior to autoignition. So on the left, again, I'm showing you imaging from Scott Skeen, who did these visualizations in the same rig, Lyle Pickett's high pressure combustion vessel. So you're looking at the flow just prior to autoignition, the cool flame regime, and the hot ignition regime. On the right, what we're trying to do is, with the LES, is step one is identify where autoignition is most likely to occur by finding where the ignition delay time, scalar dissipation rate, and strain rate are simultaneously minimized. And the three plots on the right are what show you that, just prior to ignition for this experiment. Then once you do that, we can identify the variations that occur in terms of properties, so say temperature, equivalence ratio, and pressure in the flammable regions. That then lets us start looking at what we might want to do in terms of chemistry. So the last point I'd like to make is the fact that in the following way. So the key mechanisms that one might consider, at least as the either full or skeletal and so on, are the ones I'm listing here. And these are fairly well known, so I won't take the time to talk about them in detail other than to say, depending on the combustion model we're selecting, we might want to use any one of these, and ultimately we might want to use a mechanism, perhaps even in the DNS context, that actually reduces the number of species and reaction steps we have to carry to something very small, typically on the order of 25 or 25 species. What's interesting about this is the fact that predicted ignition delay times, for example, between mechanisms, even within the design ranges, do exhibit various discrepancies as a function of how they were tuned and so on. And this becomes more apparent if we get off the log scale that I'm showing here, and then these are the same mechanisms I listed on the last slide, all tuned for a different reason. But now if we look in particular at the plot on the right, you can see that each of them predicts significantly different ignition delay times. So the real question then becomes, what's the best way to approach chemistry, depending on what we're looking for. And if we're just looking for a few select properties associated with these mechanisms, we're asking the question, can we take advantage of some of the newer UQ techniques that are being used in collaboration with people like Combustion and so on, to actually come up with designer mechanisms, so more engineered mechanisms that will do the job for now. And this slide highlights what the approach is. So it's start with the simplest mechanism possible, use Bayesian inference to find the PDFs of key model parameters, etc., and then calculate the most probable surfaces using these techniques and add complexity as needed. And we think that'll serve two purposes. One is, the first is to give us at least some idea of where the uncertainties are in these mechanisms, just to help illuminate them from a modeling perspective. And then second is it'll help select what different modeling approaches might be more optimal given the cost and of course the significant cost of chemistry. So last slide before the summary is, this is just to highlight, we have taken a first cut at very simple mechanisms to look at autoignition, and these are just some initial cross cuts that I don't want to say too much about, other than we're just following the same systematic path that I tried to convey in this presentation. Summary, and I'll just go through the bigger bullets, is we have a new theory that I showed you to explain experimentally observed differences in liquid injection processes at elevated supercritical pressures. Second, using the insights gained above, we focused on the effects of detailed thermodynamics and transport using a real fluid model in LES, and we focused on the spray A case there. Further analysis beyond data we could get from the experiments helped reveal the flammable regions just prior to autoignition and the related envelope of pressure, temperature, and equivalent ratio that we need to be concerned about from a mechanism performance perspective. And last, given the uncertainties in the full and skeletal chemical mechanisms at conditions of interest, we're investigating the merits of optimizing simple mechanisms over known pressure, temperatures, and equivalence ratios using advanced UQ techniques. And so thank you very much. And once again, I apologize for not being able to be here in person, but hope to see you all soon at other venues. Thanks.